Earlier, we've learned how to look for perfect squares by looking at the factors to see if any of the factors are of a perfect square. So we're going to use this idea to help us look at factors that are perfect squares or cubes of variables. Before we get to there, we're going to move forward from this point in time and assume that when we're dealing with any non-function, we're going to assume that we're going to be dealing with non-negative numbers in a radicand, and in that case, we're going to produce an A. We're going to drop the absolute value. So for now, we're just going to assume that we're going to work with a positive result. So how do we find out if, for example, the square root of 6, the square root of 6 to the x, the square root of x to the 6th, how are we going to know if that's a perfect square? Or how to identify a perfect square? Well, if we remember that we can rewrite this as x cubed to the square, and that allows us to eliminate the square root and the square, and I'm left with x cubed. Again, we're dropping the absolute value, so it's just x cubed. So x to the 6th is a perfect square. It is x cubed times x cubed. Another way to look at that too, if I wanted to rewrite this as x to the 6th to the 1/2, I'm going from root world to exponent world. Work with an exponent world, that becomes x to the 6 over 2, which makes it x cubed. So again, I see that this is a perfect square. And my clue is that if the 6 can be evenly divided by the index, then I know I have a perfect square or a perfect root of some type. Let's look at another example. Say I have the cube root of 21. X to the 21st. I got a little ugly there. X to the, well, my example I use y. What we do with y. The cube root of y to the 21st. Was y to the 21st, is that a perfect cube? How do we think about that? Well, we can rewrite that as a cube root of y to the 7th raised to the 3rd power. Because remember, exponent to an exponent, we multiply. Here, if I follow that model, I'm raising a root to the same power as its index. That just becomes the radicand, which is y to the 7th. Or, if you want to work with it in exponent world, this becomes y to the 21st to the 1/3 equals y to the 21st over 3, and that also equals y to the 7th. So y to the 7th is a perfect cube. Or I'm sorry, y to the 21st is a perfect cube. And again, the clue is, does the 21st divide by the index evenly? That shows me. Now let's look at one more. Let's say we have the 6th root of z to the 24th. Well, I'm expecting z to the 24th to be a perfect 6th root, because 6 divides into 24 evenly. Looking at the same process, let's convince ourselves of this being the case. I can rewrite this as the 6th root of z to the 4th all to the 6th. Following our model up there, I'm raising to the same as the index. I'm left with z to the 4th. Or rewriting this as an exponent, if I would choose to, that could be z to the 24th to the 1/6. Multiply the exponents. Z to the 24 divided by a 6 equals z to the 4th. So one of the difficulties we're going to have as we're moving forward is to understand what are perfect squares, cubes, and so forth with numbers or constants, but also to what are perfect squares, cubes, and so forth with variables raised to a particular power. It's the same process, but we're still going to get confused a little bit if we don't practice.